Hi, I'm Daniel from the Airborne Radio Collar Tracker team, and we have Thomas, Naveen, and Sam also on the team that will talk a little later in the presentation. So, a bit of background. Researchers from places like the San Diego Zoo would like to track movement patterns of wildlife to find out things like their population size, their habitats, and other metrics like that. So, our project, the Radio Collar Tracker project, basically puts a small radio collar on these animals that emits an RF ping periodically. We then send a copter overhead with a mounted antenna that will listen to these pings, and based upon that signal strength and their GPS coordinates, we'll be able to correlate exactly where those animals are. So this is an improvement upon previous methodology that included a handheld antenna and would cause the researchers to have to walk through some pretty treacherous terrain. So we've actually had some previous deployments in the Dominican Republic and Cayman Islands, which has had a good amount of success, but this quarter we wanted to improve it even further. So we improved upon 3 specific applications that would ensure the success for future iterations to come in this project. So now we're going to turn it over to Dr. Vineyard and Dr. Ann in the lab to do a live demo of some of these improvements.
Thank you very much, Dr. Knapp. We are live here from the one and only C-Lab CSE 2127.
Yes, we are extremely excited to showcase our improvements to the radio collar tracker that we've made in the past quarter. These improvements include a new GPS parsing script, a new user interface, and a radio collar emulator.
Now, fortunately, we're actually lucky enough to finally have the 3DR Solo, our drone platform, available in-house for a live demo. Sorry, hold on one sec. What do you need? I'm in a live demo. What are you saying the drone platform isn't available? Still stuck in the Cayman Islands? That means we have to use the stunt drone. Moving forward, our products for this quarter were actually loosely coupled with the drone platform, the 3DR Solo, and in fact it was modular in design and implementation.
Yes, we'll give a quick little demo of the web interface developed on the Intel Jewel, which is a Linux microcomputer, and it's essentially the brains behind our radio collar tracker.
So in the top half, we have the web interface. In the bottom half, I'm actually accessing the terminal of the Intel Jewel and manually providing status check outputs as well as recording the data logging input from the web interface. So real quick, I'll demo a status check output. And you'll see here the first icon will turn green, indicating a successful status check, and I'll record a data logging input that the bash UI script will use to start data logging. And now I can check the status text file to see that the last digit is now a 1, indicating that the data logging input was recorded successfully. Alright, well I hope you enjoyed that exhilarating web interface demo. I know I did. Got something better to show you. A GPS parser for the uBlox M8N excellent GPS module. So I've actually already recorded and parsed the GPS data from the module. As you can see here, these are the contents of the log. I'm actually going to use a Google Map Python library to generate an HTML file from these coordinates. So you can actually verify the path that I took around campus simply driving around with the GPS module. Yo, Naveen, we're in the middle of a live demo. Did you have something super cool to show?
Oh yeah!
Let's get going.
Since collars break over time and we have limited access to them, the last improvement we did was to build a radio collar emulator. We used a software called GNU Radio that provided us with signal processing blocks for the software-defined radio. First, we needed to recreate the signal of the radio collar. To do this, we created a block in GNU Radio that will perform the pulse width modulation technique. And using GNU Radio, we were able to adjust the frequency, amplitude, and the pulse width of the signal. And if you simulate this, that's the pulse that we're creating, and if we can compare it to the actual radio collar on the left. Someone's at the door.
Oh, hey man, almost forgot I have something to show too. We analyzed the collar's transmitted signal by breaking it down into 4 characteristics. Pulse width is the length and time of each pulse. Pulse period is the time between pulses. Frequency content contains the frequencies the collar transmits at, and amplitude profile is the strength of the signal over time. We combine these characteristics to make our emulated signal. Okay, great. So we have our GPS pipeline that's so modular we'll be able to take that from any platform and put it on another one with very minimal effort. We also have our web UI that's very easy to use for non-engineers specifically and is also very extensible. And we have our collar emulator that will essentially allow us to emulate any collar we want without worrying about collar degradation. So with these three things, we think we've added a great deal of value to the project this quarter. Thank you for your time. Love you, Kastner. Nap out.